introduced in the physics literature like 40 years ago by a Russian physicist named Polyakov. It was designed as a model for two-dimensional bosonic string theory and quantum gravity. So in defining this dual theory, Polyakov introduced a natural way of picking at random geometry on a surface whose topology is fixed. So I think the connection between quantum gravity and random surfaces is rather obvious. Connection between random surfaces and string theory is less obvious, and this drawing explains a little bit where this connection comes from. So what you see is that the worldsheet of a string is essentially a random surface because string is deterministic. So first, this dual theory has been studied a lot in physics literature. This paper by Polyakov has initiated a very huge amount of work in the physics community. So for instance, 3 years after this initial paper, there was this work by BPZ on two-dimensional conformal field theories, which is one of the most cited papers in physics, I guess. 10 years after, there was this DOZZ formula for structure constants of field theory, which is. So yeah, I put a lot of acronyms. So this stands for the Russian physicists named Belavin, Polyakov, and Zamolodchikov. DOZZ stands for Dorn, Otto, Zamolodchikov, two brothers. In 2007, I guess, the AGT correspondence, which provides a link between dual theory and certain fundamental goal theories. So far it's only for the physics picture, but mathematicians are not interested in this CFT too, especially over the past decade. So there are many work teams that have been interested in this CFT. So one of them is the making of trace community with this famous initiative by this famous paper by Duplantier and Jeffy in 2014. There are also approaches come more from discrete picture and mostly based on statistical physics. Like for instance, Le Gall, Mirmont with the Brownian map. Yeah, but the framework I will follow in the second will be the one introduced by David Kupinen, Rod and Vargas in 2014, and which is closer, I guess, to the work Polyakov designed in the 80s. So our next question is, okay, I've given a broad picture of this Lewis theory, but what are they? What is this Lewis theory? Okay, so Lewis theory is a theory of random surfaces. So the aim of this theory is to define notion of random surface. So in this paper of Polyakov actually reduces the problem to, with many simplification, to defining a law of a random field. So essentially, this is a conformal factor of the surface. So in order to define a random surface, the problem is reduced to defining the law of a random field, a random function, and not some surface which is fixed. This quantum field, the very nice thing is that it is defined using a path integral approach. This means that the random field will be defined with an expression like this. This is quite common in the physics to have this type of definition, this path integral approach. But this, from the point of view of mathematics, this approach lacks rigorousness. So, for instance, this you have an integral which runs over all the functions of a surface, and this d phi should be like some Liebig measure on this set of functions. So, this does not really make sense. So, from the point of view of mathematics, providing a rigorous notion to this path integral approach is not really easy. But the miracle which happens for Lewis theory is that the functional, the action which is involved has a very nice form. I will explain later why this is really nice to have this type of action functional. So, question is how to make sense of this path integral? I mean, rigorously. Okay, if you recall a bit of probability from, I don't know if I've done this, but you see that in this action, you have a quadratic part. And this quadratic part, it's reminiscent of a Gaussian integral. If you remember to define a Gaussian vector, so basically you have this e to the minus x squared over 2 for a Gaussian random variable. If you have a Gaussian vector, it's a scalar product of x, a covariance matrix minus 1x. So here you can think of this measure as a Gaussian measure. Actually, this is the way we interpret the first part of this path integral using probability. And so you have this Gaussian free field, which is universal in probability, which naturally arises in this interpretation. So you see that here the Gaussian, the green kernel of this, which is the covariance kernel of the GFF, is nothing but the inverse of the Laplacian. So this is exactly the same thing as the Gaussian vector. So this Gaussian free field, it's a random distribution, so it's not really a function. It's not well-defined pointwise because the green kernel has divergence on the diagonal. But you can think of it as a random distribution. So in the end, we may, using probabilistic tools, we may interpret the path integral as follows. So you have this, so we have absorbed the quadratic term in the Liouville action, and the only thing which remains is the other parts, which was the potential. So, okay, there's one subtle issue here, is because this, you take the exponential of the distribution, and this does not really make sense. So we need to do like this Gaussian multiplicative chaos renormalization. So basically, what you do is that you use a regularization of the field, you exponentiate it, you see that fluctuations of this of the approximation has some nice scaling, and in the end, if you use an appropriate renormalization, you have a well-defined limit. So this exponential gamma x will be a random measure. And it's called a Gaussian multiplicative chaos or Liouville continuum gravity measure. It depends on who you're talking with. And in the end, so the result by David Pippen and Roland Vargas in 2014 was that this defining the probability, this path integral using these probabilistic tools, the result defined was indeed a CFT, and it was consistent with some properties of the CFT, namely the one anomaly mentioned later on some property on vertex operators. Right, so far from Liouville, is everything all right? And I can move to the theories. Quite quick. So second part of the talk will be to go from this Liouville to Toda CFTs. So Toda CFTs are a family of two-dimensional conformal field theories, which are indexed by semi-simple and complex algebras. And the very nice fact about this theories is that they provide natural generalization of Liouville CFT. Liouville CFT corresponds to the case of the rank 1 special linear algebra, so SL2. Nice property is that they are defined using a path integral tool. So you have an action functional, which is really similar to that of Liouville, but the field that you want to define, the quantum field, the random function you want to define, has no values in some Euclidean space. So namely, this Euclidean space, if you know a bit of the algebras, I don't know, it will be the Cartan subalgebra of underlying simple algebra. So you can do the same thing with Toda series, and in the end, you can interpret everything in terms of probability, and you end up defining a conformal field theory. And the central charge is, again, like be expressed in terms of the background charge. So don't put details because it's a bit long to explain like this, the algebra things. I just ask you to trust me what's. So next question is, okay, we are very happy. We have defined our theory, but the question is, how can we understand these theories? Yeah, so basically what we mean by understanding theory is like to have some integrability properties. So This means that information on the model is available via certain observables, which are called correlation functions. And what you do, if you want to understand like this model of CFT, you want to compute a correlation function of vertex operator. So this takes the form, in theory, this are of the following form. So you take some vertex operator. So these are vertex, so-called vertex operators. And they depend on a weight, alpha, which is an element of C. So here, alpha is in C. In the case of Liouville, but in the case of Toda, it would be the carton subalgebra. This Z will be elements of the underlying surface. And so the problem of understanding the series is reduced to computing. So this is the expected value with respect to the path integral of this vertex operator. And in Liouville and Toda theories, these vertex operators are the form, so V alpha of Z. They are defined using the quantum field. So what I mean by computing correlation function is that you take some alpha, take all the possible alpha, you take all possible value of Z on the surface, you take this function of the field, so this is a function of the random field, and you take the average of this product of vertex operators under the law. So you take the average with respect to the law of the probabilistic, so the Gaussian free field. And so the main goal is to understand how to compute this correlation function of vertex operators. So this is where the machinery developed by BPZ, Bellavin, Polikov, comes into effect. So in this groundbreaking paper in 1984, they developed a model for such as which, like Liouville theory or Toda theories, are conformal field theories. That is, they enjoy a certain symmetry. And basically, the assumption of BPZ was that so we can in the physics, in a model which comes from the physics, it was possible to find a representation of the Virasoro algebra, which is the algebra of symmetry of two-dimensional CFT. So basically, what you do is first you understand Virasoro algebra. You understand. You see, you study representation theory of Virasoro algebra. This will have consequences on these correlation functions. And then, yeah, you go from the algebra, the world of representation theory, to your physics model using some assumptions. And this is where we disagree with physicists. Namely, so for instance, what BPZ did was to develop, so they say that the Virasoro algebra, the method, the representation theory of Virasoro algebra, then what they implied was that there were mostly two aspects. So the first one was a method to find certain identities. So the fact that there are conformal symmetries in a model leads to certain identities between correlation functions. So you have word identities. So these are word identities are certain differential equations for this satisfied by these correlation functions. And the next one is conformal bootstrap, which is a recursive procedure to compute all correlation functions on so-called structure constants. And this essentially, so this is the approach used by physicists to prove integrability properties for CFT usually, at least for Liouville CFT. And what Cerclé, Roland Vargas, and Guillermo Roland Vargas proved like in 2017 and 2020 was that the probabilistic model was consistent with the assumption of BPZ. of the made in the physics literature, and it was possible to implement the machinery developed by BPZ in dual theory. And what they did was to provide a rigorous proof of the OZZ formula, which are the structure constants of QV CFT. 2020, they proved conformal bootstraps. This is the achievement, yes. And yeah, 2 weeks ago, they also proved like this Segal axiom that the CFT was also satisfying this Segal axiom protection. 2 minutes, I guess. Okay, what happens to the last series? In 2 minutes, too short. The nice thing about Toda theory is that in addition to conformal invariants, they enjoy an enhanced level of symmetry. That is, they are conformal invariant, but in addition to that, there is another level of symmetry which is prescribed by W symmetry. And this, the algebra of symmetry of Toda series is W algebra, which we may have heard about. Yeah, I hope. So you can basically do the same thing that BPZ developed using the other algebra in the case of W algebras. That means that you can have similarly one identities and yeah, perhaps conformal bootstrap, but it's not really clear at the moment. And so what we did with Yishao Long last year was to prove that it was indeed consistent with results expected in the physics literature. That is, we proved that this type of identities was also true on our progressive model. We also proved like this BPC type differential equation, which is the starting point to integrability of Toda series.
Thank you.
So, yeah, just to give some overviews. So, next project will be to compute Toda structure constant. So, with Yishao, we've proved this BPZ differential equation of identities, and the starting point to prove like this. Yeah, to compute structure constants of Toda series, but there are many complications, especially from the probabilistic point of view. There are many interesting things to be done. Next step would be also to carry out the bootstrap machinery for Toda series, and this is far from obvious, even from the literature. It's really interesting from the scattering theory point of view. It will involve like scattering of yeah, so kind of Laplacian and Weyl chambers. So it's really interesting. Not the time to talk about that. So thank you for your attention.
Questions? Yes.
So does this Gaussian multiplicative chaos generalize in this kind of higher dimensional target space?
Higher dimension, you mean? Or in
Yeah, because now your functions there are like two some.
So basically, you have several Gaussian multiplicative chaos. So instead of having one Gaussian free field, you have several Gaussian free fields. A family of, so you say that R is the rank of the algebra. You have R Gaussian free fields, which are proposed in a way prescribed by the Cartan matrix of the algebra. So you have several Gaussian multiplicative chaos. And from the point of view of probability, it's a bit a mess because you have really a lot of term computations that we see. Yeah, so.
More questions? So is it true that this probabilistic method applies for large central charge, like C bigger than 25?
Yeah. So
is there any progress for smaller?
Yes, so there have been some progress for central charge less than 1, but it's not
less than 25. Between 1 and 25.
Between 1 and 25, it's not clear.
Okay.
Less than 1, there is it's a different approach. It's using CLE instead of. I mean, the school by developed. The MIT school is working on that. So they developed this CLE for. It seems that it's somehow worked Yeah, to compute structure constant for field theory for central charge example.
Okay, more questions? If not, let's thank the speaker. Sorry, what was that?
Sorry, question. I mean, I guess in the physics literature, the large n limit of SLN or GLN Toda theories has been considered. Is there where you send n to infinity and then you consider this phi I to?
Yeah, I think that exists, but I'm not.
Okay, so there's no math.
So I think from the probability point of view, it will be interesting to develop to define these models. But at least what we've done with ISO was on a SLS3 case, and computation was so horrible. I don't think we'll even do like SL4 or.
I mean, sometimes the things become simpler when you take enlarge. I mean,
Yeah. Yeah, but you won't ask the same questions. I mean, proving wall identities will be a mess. But
you have a W infinity symmetry then, right?
yeah. So you have an infinity of tensor.
Okay. So thank you very much.